The presentation today is about the whys and the how about decarbonization, electrification. We are most certainly at one of the most interesting times in our careers, but it's not a new subject, is it, John? We've been talking about this for a long, long time. It just so happens the timing is perfect, and we were discussing on the way from the airport here, there's never been a better time in this industry for everybody here in the room. Whether you're from the engineering community or the manufacturing community, government, whatever it is that you're doing, the trades particularly, this is a moment in time that you will never see again in terms of the opportunities. And there is a huge knowledge gap that exists between what the world wants in terms of decarbonization, electrification, and how we actually get there. And the trades and the manufacturers and the engineering community, of course, are a big part of that. So it's good to have you here. At some point, it would be nice to have literally thousands of people participate in these education programs, because if we don't educate the industry, we're going to be seeing a big train wreck. Anyways, I want to talk about energy. My job is to talk about the why we need to do it. And it's really interesting when you think about the intuition that people have when they use energy. We actually come with really good intuition. We know what is an appropriate tool for the job. We know the difference between a non-industrial tool and an industrial tool. So no one would, hire a backhoe to do gardening. No one would use, a 25-pound sledgehammer to pound in a finishing nail. That's an industrial tool for a non-industrial application. Some of you might use a combine for your lawns, but most people aren't going to use a combine to cut your lawn. You're going to use something else, a more appropriate tool. For those of you that like to, tenderize your meat, maybe you actually need the packer, but you're not going to use a compression tool like that. You're going to use something that's more attuned for the task, a non-industrial tool. We certainly aren't going to use a heavy snow plow to clean the snow off your patio. These are it's intuition. We know what is a right job for the task. You would never bring the fire department to come, water your lawn. We all come with a sense of energy constipation when you get behind a slow-moving vehicle, how you want to go faster, but you can't. We know people come with an intuition about exhilaration, energy exhilaration. So we come with this sense about what is right, what is wrong, what's a non-industrial tool, what's an industrial tool. And we have that, and for some reason when it comes to architecture, our brains go dead. We don't understand that when we take a hydrocarbon, particularly natural gas, and we turn it into a flame that we're generating, something like 3,100 degrees, 1,700 degrees Celsius flame temperatures, when all we need to do is to condition spaces to around 70 degrees Fahrenheit. Combustion is an industrial grade process. It creates industrial grade temperatures. We don't need those temperatures. So when you think about the flame temperature, the combustion temperature of gas, propane, anything that's in the hydrocarbon range, those are good tools for industrial processes, like making steel, like moving ships, like flying planes. Those tasks require high quality fuel. But when we're just trying to heat spaces to 70 degrees or domestic water to 120, those are nowhere near industrial grade processes. Not even close, like a magnitude of order difference between an industrial process and a non-industrial process. And so the problem that we have is that all over the world, governments are promoting conservation, 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 and that's a good thing. But if you're still using hydrocarbons, even if you reduce the use of the fuel and you're still using it for non-industrial purposes, it's still a destruction of its potential. And so that whole concept is flawed. There's benefits to it, yes. But we can't keep using high-quality fuels, high-quality energy for non-industrial purposes. So I want to give you a quick lesson on what I'm about to talk about. Now, everybody that's in the heat pump business understand or knows something about the heat pump engine, the heat engine. Carnot and his concepts about if you have a reservoir of temperature over here and you have another one over here, that between the two, if there's a differential, we can actually do work. And if we put energy into that process, we can actually reverse it. Thus the heat pump. That was back in the 1800s. Well, following him was this guy named Joule, who developed the unit, the joule. And he was the guy that said, well, you know what? Work and heat are associated elements. They're almost identical. So when we convert one energy form, in this case gas, to a thermal, to a heat, yeah, we can get high thermal efficiency out of that conversion. But we can do a whole heck of a lot more with that conversion other than just heat. And so he started to introduce this topic, which is called Exergy efficiency, not energy efficiency, but Exergy efficiency, where you take a unit of something, in this case, let's say gas, and you convert it into a flame, so it goes from a chemical energy to a thermal energy, and we can get high efficiency out of that process, like 97%. But what else could we have done with that same unit of gas? We could have took that same unit of gas and we could have taken water, turned it to steam, used the steam to drive a turbine. From the turbine, we can generate power, and then through a series of cascading heat exchangers, get the temperature down to where it's actually useful for space heating. We actually use its fullest potential. That concept is called Exergy efficiency. And so Gibbs comes along. Gibbs, by the way, Einstein said he was the greatest mind America ever had was Gibbs. And he started to take this concepts about converting energy from one form to the next, and then what do we do with that conversion process? Later on, this guy, Rant, coined the term Exergy and energy, but we're not going to talk about that today, but Exergy and Exergy efficiency. So when we take that unit, whatever you want to measure it in, a cubic foot, a gallon, a barrel, whatever it is, and we put a flame to it, light it up, it can do thermal, but there's work also available in that same conversion process. And so we know that thermally we can get 97% out of a boiler, but it's Exergy efficiency because there's a lot more potential in the gas. On a good day, might get 6%. And that's where we're at today. We have to stop taking high quality energy and using it for low non-industrial purposes. We can still use gas, there's lots of great processes for it, but we don't need to use it for space heating and cooling. To bring it down into maybe another concept, if you take a glass of water that's extremely hot and let that represent combustion, and you put it in a room, the heat will want to flow from hot to cold, eventually reaching an equilibrium with the other reservoir. So you have one reservoir and two reservoirs, and the energy will move into the space. But you can do the same thing with solar, which is at 220 degrees instead of 3,400 degrees. And if you want to move energy from the room into the earth, or use the earth as a sink, again, it's a very narrow band relative to the large band or the large differential that's created with combustion. So the logic behind decarbonization, electrification is really about, are we using the appropriate energy source for conditioning buildings? And the answer is no. So what I'm going to show you next is a series of energy resources that we have on the planet compared to combustion. Now, this is a cooling tower at a cooling plant. It's the biggest oxymoron in the world. There's nothing cool about a cooling tower. When you look at it through a thermographic image, you can see the heat and the mass. And of course, associated with this process is sound and vibration. And all of that we can call the disorder of the conversion, which is called entropy. When you look at the entropy of other energy sources like geothermal, or you compare it to, say, wind power. That, by the way, is my son. It was his idea to jump the fence, the one that said no trespassing. It was my idea to bring the guns. It was a good day. What we wanted to do, we wanted to see the size of the nuts and the bolts on a wind turbine. Have you ever seen them, John? They're monstrous. Like they must weigh, I don't know, those nuts must weigh probably 7-8 pounds each. But they don't have the signature that a combustion plant does. Hydro does not have the same combustion signature. When you think about photovoltaics or even the thermal systems, these are all low entropy systems. The energy conversion is way more aligned to the needs that we have for conditioning people and buildings. And even today, now, we're starting to see a lot of non-compressor-based cooling systems. This one here was at one of the universities. Peter Rumsey was the engineer on it. What they do during the evening is they spray water up onto the roof. And they cool the water with radiative cooling and evaporative cooling. And they store that chilled water in a cistern. And then during the day, they take that chilled water and they cool it with a radiant floor cooling system. No compressors. There's new technology out, and this came, I believe, out of Harvard. This is not a solar absorber. This is actually an emitter. It's actually emitting energy during the daytime into space. And we know when there's a differential temperature, which there is during the daytime, that you can actually discharge energy into space during the day. So this has just been commercialized. This was their prototypes. And there are some big, big companies involved in this technology. Again, cooling without compressors. So I want to talk about two projects. Back when I was a young man, a gentleman by the name of Don Holt, who was the ASHRAE president at the time, had a company called Vision Wall. And Vision Wall, this was back in the 80s, early 90s, was making high-performance glass before anybody even knew what high-performance glass was. These windows, again, this is a long, long time ago, at least R7, R8. Like, these were high-performance stuff. And I went in to go see Don, because we were representing controls, hydronic controls at the time. And I went into Don's office, and Don was like this, brain power, sitting on this, chair, and I was this young, stupid man. And I wanted to see if we could get the contract to sell him thermostatic radiator valves, because that's what everybody did in Edmonton and high rises. Boiler risers, thermostatic control valves on baseboard systems. And he said, Robert, we're going to use electric radiant sealing systems. I had never even heard of electric radiant sealing systems at the time. And I went, what? What? This is Alberta. Like, we live and die on oil and gas. We don't use electricity to heat our buildings. He said, we are going to build a high-performance building, and we're going to heat it with electric radiant sealing panels. So because I was young and dumb and revered Don Holt, I just said, okay, I guess we're not going to be using hydronics on this job, and wished him well. That job still exists today. It is a load on an electrical system that generates power with combustion, coal and gas. And every time the meters turn in that building, it's contributing greenhouse gases to our environment. Someday, the energy systems in Alberta will catch up with that building. That building is ready for the future. But in the meantime, it hasn't actually been the most, the contribution that it makes to our environmental systems has not been stellar. Let's put it that way. One province over, Manitoba Hydro Building. I've been in this building several times. By its very nature, you can tell that the company is involved in hydropower, right? High performance building, radiant heating, radiant cooling throughout, dedicated ventilation systems, displacement. It's a beautiful, beautiful structure. Low entropy, hydro, running heat pumps in a high performance building with radiant systems. It doesn't get any better than that, right? And I happened to be downtown, and I actually turned around with my camera, and there it was, the old chimney up against the solar chimney of the building. Anyways, if I had more time, I would talk about that. So there's two buildings, both electric, one being fed off a combustion-based network, and the other one based off of hydro. Completely two different stories. So if you look at the load or the generation in Manitoba, almost 97% of the power generated in Manitoba is hydro, low entropy systems. It's the perfect energy for that province and for many parts of Canada for driving power into heat pumps connected to large surface area heat exchangers in high performance buildings. That is the best it will ever get in our lifetime. Relative to Alberta, which is going to be a holdout, eventually Alberta will get there, but you can see our energy is generated somewhere else. So it's not just a matter of putting electric into a network. How is that power generated? So this guy, you don't need to read this, but at the age of 21, right, Oxford University makes a special condition so that he can become an Oxford Research Fellow at the age of 21. I don't know about you, but at the age of 21, I was running from my girlfriend's boyfriends and trying to stay out of jail. This guy becomes an Oxford research fellow at the age of 21. Then at 29, he tells them to go pound sand. I don't know anybody that earns a fellowship and says to the organization, yeah, you know what, I'm done. I'm giving up my fellowship. Like, it just doesn't happen, right? Starts the Rocky Mountain Institute. And he starts to look at the things that Gibbs was talking about, and Joule and Carnot and all these other individuals about converting energy. And he writes this paper, this book. This is 50 years ago he writes this. And he says, we are at a time 50 years ago that we need to make a decision. And if we make the wrong decision, we're going to be in trouble in 15 years or 50 years. So here we are 50 years later, and we are in a problem. This is what he saw. He saw we need to go to renewables, low entropy systems, wind, photovoltaics, solar thermal, right? These types of projects. Drake Landing, just outside of Calgary, right? They take heat from the sun during the summertime, they dump it into a great big solar battery in the ground. And then during the wintertime, they pull that heat out of the ground. Low entropy, very little waste heat, no vibration, that type of stuff. One would think that if you have a process that's generating heat and power and you've got waste heat and you've got buildings around it, that you would like marry those together, right? That makes a ton of sense. But it doesn't happen. But this is the kind of stuff that Amory was thinking about. Today we have power plants. They run 24/7, 365. If you live in a cold climate like many of us do, you can see it run. If you don't live in a cold climate, maybe you don't see it, but it's still there. And there's thousands of these plants all over the world. You can see the thermal plants running during the cold time, but this happens all the time. Even though you can't see it, it's going on. And as a result, we have the greenhouse gas emissions climbing. Now, I'm not a climatologist, I'm not a geologist, I'm not an oceanographer. I don't know a lot about the climate, but I do know over 40 some odd years, I can look at a graph, and even if the graph is 20% wrong, it doesn't change the picture. Right, John? Right? You don't have to be a statistician. Maybe you're a conspiracy theorist and you don't even believe that greenhouse gases are an issue and the data is wrong. Even if the data is wrong by 20%, it doesn't change the message. So many years ago, about 10 years ago, actually, I had to come here for Vancouver for a conference, and they wanted me to talk about what I saw happening in the future. And I said to look at the future, I wanted to look at the past. So we went into our inventory of all the buildings that we designed over my career, and we started to look at what were the characteristics of the building, the loads, the type of the heating system, the temperatures that they operated at. And we started to develop a graph, and that graph started to tell a picture about how we build buildings and the temperatures that we use in buildings and the type of heat exchangers that we use in them. And what we started to see is that over time, the temperatures kept getting lower and lower and lower in heating, and higher and higher and higher in cooling. And the reason why we were seeing this profile change in temperatures was because the building performance were getting better and better and better, and we were starting to use larger and larger surface area heat exchangers. And we got to the point, not that long ago, where we could actually condition buildings with temperatures that were lower than what we found on the human body, less than 100 degrees. We don't need 120 or 130 or 140 degrees to condition buildings. We can do it with less than that. One of the best stories I have in my life, we did a project for Hydronics just west of Calgary, or east of Calgary. And we worked with them on their architecture, their enclosure, their designs, and the mechanical systems. And we got them to build a high-performance industrial facility. It was like 75,000 square feet. I was down in Arizona. I get a call from Andy. Robert, how you doing? Hey, Andy, how you doing? I'm doing good. He says, it's minus 40 degrees here. I go, wow, that's cold because it's really nice here. And he says, Robert, we're actually heating the building now, 75,000 square feet with 90 degree supply. It's coming back to the boiler around 82, something like that. And I want to lower the boiler. Can I do it? And I went, you want to take the temperature down? He goes, yep, we want to take it down to around 80 some odd degrees. And I said, that's what it's all about. No one calls you up at minus 40 and says, can we lower the temperature? They always want, can we crank up the temperature? I said, nope, go ahead, Andy, drop her down. So he was able to get those boilers to do exactly what they were doing. But there was still lost work potential in that gas. So we started to plot this on this graph. We looked at the temperature profiles in spaces, where are the non-industrial temperatures, where are the industrial temperatures, what's in between, which is where typically you would see most HVAC systems operating. We looked at temperatures that we needed for cooling, dehumidification, and then we started to look at temperatures that we needed for domestic water, makeup air units, radiant, dedicated outdoor air systems, and we started to plot this graph. And then we said, okay, well, let's look at the trend that's occurred over the last 50, 60 years in district energy. So the first generation of district energy systems were steam, high temperature, high-powered systems, and then they started to shift over towards boilers and then condensing boilers. And so over a period of time, we started to see the return temperatures start to drop. And because of that, of course, our efficiencies go up, combustion efficiencies go up. So it's taken us from mid-efficiency up to high efficiency. But we still have this wasted work that's done even at these low temperatures when we use combustion. So we have to get away from that. So in this temperature range, the ideal temperature range for supply and return is when we can start to get into the world of heat pumps and non-compressor-based cooling systems. And it just so happens that that's lower than the temperature on the human body. So we said in that paper 10 years ago, we could actually almost get rid of most energy documents, codes, standards, that type of stuff, and just say, no building shall be designed with temperatures that are greater or less than 77.5 degrees Fahrenheit plus or minus 22.5. And if you did that, then it would force architects and engineers and interior designers and property developers to build high-performance buildings, get the temperatures down, use large surface area heat exchangers, whether it's radiant floors or large coils in the air handlers, and we could get these amazing, amazing, not energy efficiency, although it's there, but these amazing exergy efficiency. So then we sort of categorized, okay, well, let's look at the old crappy buildings, and they had really high loads, over 30 BTUs per hour per square foot. They had small surface area heat exchangers, baseboards, fan coils, that kind of stuff. So they needed the high temperatures. Well, those high temperatures create a whole bunch of problems. A, you couldn't get the efficiency out of the boiler. You certainly couldn't use a heat pump. And it created stratification and drafts and all kinds of thermal comfort issues in them. And then as soon as we get into the low temperatures, get into the low loads, less than 10 BTUs per hour per square foot, now we can start getting these really low temperatures in heating and high temperatures in cooling, and the same thing on the cooling side. And when we can start to get these low temperatures in heating, say 70 degrees coming back to a heat pump, or 70 degrees coming, or 72 degrees or 68 degrees back to a heat pump, all of a sudden magic happens in terms of the COPs and the efficiencies. So this whole concept about designing systems, you're not, and this is one of the reasons why I'm grateful to have this opportunity to talk to you, particularly for the trades here. You just can't take a piece of machinery, an engine, if you will, and put it in a mechanical room and think you're going to get the performance out of it. The performance in any heat pump that you're going to do in the future, to get the maximum out of it, it has to be engineered. And it starts with the enclosure. It means you have to get the loads down, get the heating and the cooling loads, which means you have to learn a little bit about building science. And you have to start to understand the heat exchangers, because when we increase the surface area of the heat exchanger, our supply temperatures can go down in heating and our cooling temperatures can go up in cooling. And those return temperatures back to the heat pump make it do exactly what the engineers intended it to do at the factory. So in our lifetime, now, today, all of us in the room, this is as good as it's gonna get. When you can marry or take a high performance enclosure, put in a low entropy system comprised of a heat pump married up to some kind of renewable system, marry it to thermal storage of some form and connect it to a large surface area heat exchanger, it will never get any better than that in our lifetime. And you have a huge opportunity to contribute to the future, not only here in your own location, but to Canada and to around the world. So moving from typical performances from heat pumps to these low exergy systems means you have to engineer the systems. So if you're not one that gets attracted to the math, find those in the room that do the math and work with them. But don't just think you're going to get these things to do because it says it on the label or it comes in the brochure. You have to put it in. There has to be some math done in order to move it into these ranges. So that's why we need to electrify. And the next person to talk about the how is my colleague and friend, John Siegenthaler, who just bought a skid steer. Every one of you guys are probably buying Porsches and Ferraris. John buys a skid steer. That's my man. All right, thank you.
Thank you, Robert. Well, for those that don't know me, I'm from the States, upstate New York. And with all the peace and tranquility that's going on in the United States these days, it was good to come up to Canada and on a highway ride in from the airport yesterday, see some real aggression. So I appreciate that. I'm going to follow up with what Robert was talking about. We're going to talk about kind of the nuts and bolts of how do we make hydronics relevant in this, I guess I'd call it the age of electrification. So all these things are going on, state level, federal level, I'm sure up here, provincial, even municipal levels. You've got laws going into place that are basically manipulating the energy market in ways that I've never seen before in our careers. So we have these terms, electrification, obviously changing policies on fossil fuels. Just to give you an example, in New York State, starting January 1, 2026, no new fossil fuels. That means natural gas, propane, fuel oil, gone in new construction, including gas cook stoves. That's what the legislation is. Whether they'll stick to those target dates remains to be seen, but obviously those energy markets are being manipulated, and that's good news. Robert mentioned, and I agree, this is one of the best times to be involved in hydronics. We can make hydronics very relevant to not only electrification, but as buildings become more efficient, as loads go down, we need to, as an industry, stay in the game. We don't want to necessarily give that to the ductless mini-split people. Not that those systems don't work, but hydronics can be very relevant, but it is going to take a change of mindset in terms of how we do those hydronic systems. Net zero, that's the fastest growing construction sector today. And Canada in particular, I know in Ontario, and I assume it's probably true out here in BC, it's a very rapidly growing construction market. So how do we bring hydronics into net zero? Okay, and I'll start right off at the beginning. Obviously, there's strong political opinions both ways on fossil fuels, electrification. You have to, I would ask you to put those opinions aside and look at the opportunity that you have from the standpoint of taking the technology, and I assume most of you are here because you really do like hydronics and what it has to offer, taking that and maximizing it in this opportunity that we have right now, okay? But again, it's going to take some rethinking. So why hydronics? I always like to start off with this. You know, if we're going to move heat, or for that matter, cooling around with air, we're going to do it with blowers and ducts. You know, I call flex duct the third greatest invention of mankind. It's right after WD-40 and duct tape. Flex ducts, right? And there's a reason they sell those in 25-foot lengths, and it's not so you can tape 3 of them together and make a 75-foot duct out of it. We've seen it. Now, of course, we contrast that with hydronics, much smaller conduits. You know, we call them tubes or pipes, but conduits, what we use to move the fluid that's carrying the heat. And we do it with devices that are not only physically smaller, but use a lot less electrical energy. And why is that so? And I know you probably can't read those numbers, but I'll just jump right to the point. Water is about 3,500 times better than air at storing heat. It's just what nature gave us to work with. It's nothing that we've created. So we can move a tremendous amount of heat with a relatively small volume of water compared to the volumes required with forced air. And, you know, there's a picture there. A 3/4 inch tube is equivalent to a 14 by 8 inch duct. And, of course, I made that drawing there. We call this right here, we call that Sawzall surgery. Anybody ever seen that up here? Sawzall surgery? You don't want to do that because it destroys the structure of the wood framing there. But it's a scale comparison of what we can do with relatively small tubing. And why can we do it? Because of the properties, specifically, it's called specific heat and density of water compared to those of air. Now, again, why is hydronics relevant as we go forward in the age of renewables and so forth? Well, there's a lot of benefits. I won't read them all off to you. And by the way, I'll have a PDF file. If I go through these slides a little fast, I'll have a PDF file that I'll make available to you on this. But there's a lot of good benefits to hydronic systems, okay? We can adapt a hydronic system to almost any type of device that produces warm water. We can use very low temperatures, as Robert was pointing out, very high distribution efficiency. How many have heard that term, distribution efficiency? Anybody? We've been writing about it a little bit. It's a really simple idea. You simply take the BTUs per hour that you're delivering, let's say at design load, and you divide it by the electrical wattage that operates your distribution system, not your source. It has nothing to do with the source energy. It's how much power goes in to move that heat from where it's produced to where it needs to go in the building. And hydronics is easily a 10-to-1 advantage over air in that category. And why is that relevant? You know, I think sometimes our industry as well as consumers, they get so focused on thermal efficiencies. Whether it's a COP or an AFUE rating, they get very focused on the performance of the device that's creating the heat and don't really consider the balance of the system. What's moving the heat? And again, hydronics, hands down, has the advantage there. We can integrate thermal storage. We can do thermal metering with it now. So there's a lot of things to like about hydronics, and these are all terms that we need to integrate as we build systems for these low-energy buildings. This is just another comparison. I just took a random 1 ton. If you're familiar with heat pumps, what's a ton with a heat pump? 12,000 BTUs per hour, right? So think about it. We have houses today that easily could be heated at design with a 2-ton heat pump. A half-inch PEX tube can easily carry 12,000 BTUs per hour versus the duct there at 9 inches or the rectangular duct. And, you know, there's just some photos, just that those are PEX aluminum PEX tubes, half-inch, that are run through the framing. It's fairly easy to do that. And this is what we have to do with ducting. We have to bury it within the structure. And oftentimes, a deficient forced air distribution system is the result of trying to, or simply not having a place to put the ducting. Somebody says, hide the ducting. Well, how do you do that when you have 2x10 floor joists and you have a 10-inch deep duct? It's pretty hard. So you create soffits, or you put it up in the attic and, you know, wrap it around the cords and the truss and all that kind of stuff. So I mentioned distribution efficiency. I just want to do a quick comparison. You just take rate of heat delivery, divide it by wattage going into your distribution system. So really quick, here's a very common hydronic system, boiler, 4 zone circulators. If we said each zone circulator is 85 watts, and all 4 of them were running, and then we're moving 120,000 BTUs per hour, there's the math. It's really simple. So we get this number, 353 BTUs per hour per watt. And what does it mean? Well, the way you can interpret it, for each watt that you supply the distribution system, it is delivering 353 BTUs per hour where they need to go in the building. Now, is it good, or is that average, or is it poor? What do you think? I don't know. You don't have anything to compare it to, right? You need some kind of a number to compare it to. So, let me jump over. Here's a furnace. It's delivering 80,000 BTUs per hour, and if you look up the power requirement of the blower, and I'll confess, this is a standard blower, not an ECM motor on the blower, it's 850 watts. So if we put the numbers in there, we get, and we divide, we get 94 BTUs per hour being delivered per watt of input to run that blower in that furnace. Now, here's a hydronic system concept. It's a buffer tank. Doesn't matter what heats the buffer tank. It's a manifold. It's got 8 circuits that are half-inch tube, 120 feet total out, and 60 feet out, 60 feet back. So 120-foot circuits going to panel radiators. And those are pretty big radiators. Those are 24 by 72-inch radiators. That system was designed around 110-degree water at design, okay? And if you do the mathematics of what's necessary for the circulator, that circulator at that point only needs about 8.6 watts to run, to provide the necessary flow to operate that system. And it's delivering a little over 30,000 BTUs per hour. And so the distribution efficiency, almost 3,600 BTUs per hour per watt. So look at the ratio. That hydronic system, compared to that furnace, these are 2 specific cases now, don't generalize it, is delivering heat using less than 3% of the electrical energy that the forced air system required. We need to tell that story, in addition to COP and AFUE. We don't talk a lot about the efficiency of a hydronic distribution system versus just what the source equipment is. Okay. How about this? A self-induced poor public perception of hydronic systems. This is what a hydronic system was in 1900s. I'm amazed at what the engineers created back then. You know, you look at it and say, well, that's old, that's antiquated. Well, they did things like they sloped the piping. They had very specific fittings, if you look down at the bottom there, that were designed so that just the buoyancy difference between hot water in the boiler and cooler water after it has flowed through the radiator, that's all that created the circulation in that system. And, you know, we call those gravity systems or thermosiphon systems, and they worked, okay? And you didn't need an app to run them. How do we get from that to this? And I could show you pictures all day long, and I'm sure you could. And Robert and I have reviewed, you know, the projects that come in for the Sweet Heat Contest. Beautiful craftsmanship, just beautiful craftsmanship. But, you know, again, you got to think of it from a consumer standpoint. If you go down in the basement and look on the left there, and you see all those controls, or actually in any of these photos, okay, how much does it cost? Does it break down? When it breaks down, who's going to fix it? Is there one person in the world that understands how the system operates and can service it? And what happens when that one person isn't available? So, you know, you've got to think about this, the word that gets a lot of play these days. It's called resiliency. How many of you read that in articles lately or heard that? And it's a good concept. It's simply the idea that we should design systems so that they can persevere through maybe a 2-day power outage without freezing up, okay? That they don't necessarily fail when the slightest small component might fail. You could have a system, any of these systems, where something as simple as a thermistor could fail or drift out of calibration, and it brings the entire system to a halt. That's really not resiliency. But this is where our excuse me, this is where our North American market is kind of gravitated. And again, I can't fault craftsmanship. These are, you know, excellent designs from the standpoint of putting the piping together, but this is not the future of hydronics. And if we insist that this is the future of hydronics, you can kiss the net zero market, residential market goodbye. The ductless mini-split people will take it. They already are pretty well grounded in that market. So we need to adapt to the building science, the building trends that are happening. So, you know, I'm not going to dwell on this. I'll show you some example systems here in a minute. But we can keep these systems relatively simple and still make them relevant, and it doesn't have to be complex to be sophisticated, okay? Sophisticated in the sense of how you've integrated different components and built a system that is using state-of-the-art concepts. Maybe it's outdoor reset control, maybe it's variable speed circulators, maybe it's wireless zoning using thermostatic radiator valves, I think they were called, weren't they? Yeah, and they were invented by this guy called Dan Foss. Right? Barry, you know that guy, don't you? Okay. So anyway, again, I won't read all this to you. All these things that are happening in the building market, loads are a third of what they were when Robert and I got into the market. Instead of 30 BTUs per square foot per hour, think 10. Okay? Net zero market taking off, strong consumer interest, sustainability, resiliency, recycled materials, more consumer interest in cooling. All right? That has always been our Achilles heel as an industry. Boilers don't do cooling. Heat pumps do. And you need to know that, and you need to be able to market that. Okay? Large surface area radiant panels operate at low surface temperatures, Robert was talking about here, getting that low temperature heating, high temperature cooling. Internal heat gains in these buildings are much more, they have much more of an effect on comfort. Buildings can overheat quickly when you have very low loss characteristics in the building. So all these things are happening in the, I'll say the residential and to some degree in the commercial market. What are we doing as an industry to be relevant to where these changes are and what these changes are? Okay? And, you know, I have this concept, we call it BTUs in a box. And from thermodynamic standpoint, to keep the box comfortable, all you have to do is inject BTUs in at the same rate that they're leaking out, right? You got a balance there. So from the standpoint of thermodynamics, it doesn't matter how you deliver those BTUs from the standpoint of thermodynamics. If it's 50,000 going out, it's 50,000 coming in, thermodynamics satisfied, okay? But it's not about delivering BTUs. Our job is to deliver comfort, okay? So there's the man and woman there in the hoodie footies. You know, that's what they put on when they get home to watch TV in their house while the little white box on the wall watches lovingly over them, okay? Comfort, and you know, you've got one of the world's best experts on comfort right here, so ask him questions, right? Comfort is such a complex thing. It's not just sensible air temperature, all right? It's all the interaction of humidity, wet bulb temperature, radiant temperatures of the spaces. So we have an advantage there. We can deliver comfort much better than a forced air system can. Low temperatures. So again, I won't dwell on this. Take a look at all the heat sources that are out there, whether they're heat pumps or ModCon boilers or solar panels. They all benefit from low temperature operation. That is where the global market in hydronics is going. Europeans have recognized that for decades. We're getting there. We are definitely moving in the right direction. But the future of hydronics is not 180 degree water, 200 degree Fahrenheit water. It's 100 degree water, maybe 120 degree water. Okay, and I suggest, and this is not a code or anything in the States, I suggest every hydronic system today, 120 degrees at design or lower. Okay, I go to 120, that's well within the operating envelope of heat pumps. ModCon boilers are going to work pretty well at that. That's at design. Obviously, outdoor reset control, you can bring that water temperature down. And I'm not saying you always design for 120 if you can design a system around 100 degree water. We've actually got a project, I'll talk about it this afternoon, with panel radiators. And in February, we're heating it with 90 degree Fahrenheit water. So we can design systems for, you know, definitely lower than 120, but we excuse me, we should not go over 120. And here's another thing to think about and talk about. Hydronic systems are long-term value propositions. How long does your refrigerator last when you buy a new refrigerator? Warranty period, plus 1 year. Right? How about your dishwasher, your whatever, appliances? You know, I can remember refrigerators lasting 40 and 50 years. I'm that old. General Motors made refrigerators that still lasted that long. But when we design a hydronic system and we integrate it into a building, that system's going to be there for a long time. Now, granted, the initial heat source is probably going to last maybe 15 to 20 years, and it's going to go away and something else is going to replace it. But do we want to do an extensive renovation of the distribution system 20 years down the road or 15 years down the road because we made the wrong choice today in terms of what equipment goes in there, okay? You're future-proofing your building by designing a low-temperature hydronic system, okay? And again, the PDF will show you this, but these are just typical temperature ranges for different heat emitters, and I'm going to suggest just stay in 120 or less range. There's a lot of things you can do there. Radiant panels. How many are doing radiant ceilings here or have done a radiant ceiling? How many of you do radiant floors? A lot of you, right? Probably most of you do radiant floors. Radiant ceilings, radiant walls. They can all be designed to be compatible with heat pumps and other low temperature sources, okay? And another thing that's coming, fan-assisted panel radiators. These are available in Europe. I think you're going to see them within the next couple of years in the North American market. These are little tiny fans that run on about 1.5 watts apiece when they're at full speed. They enhance the convective output at low water temperatures. So why would a manufacturer put fans in panel radiators? Because they want to sell those radiators into a market that is moving towards heat pumps and away from high temperature fossil fuel heat sources. Again, just some reference graphs you can look at later on. Radiant ceilings, radiant walls with plates, okay, and radiant floors. And that graph is just giving you relative to performance. So you can quickly estimate, you know, how many square feet would I need on a radiant ceiling to deliver 12,000 BTUs per hour, depending on, you know, obviously your water temperature. Now, please, please don't do this. Plateless staple up. I won't ask for a show of hands. We've seen it. We've had calls years ago. You know, why do you put the plates on there? The plates add cost to a system. Yeah, they do, okay? It's a 3-to-1 performance ratio. You're going to get 3 times the heat output with the plates compared to a plateless system, all right? And if you go and do this in Europe, I think in Germany, you're either put in jail or you're executed, something like that. They want to get that DNA right out of the stream, you know? Seriously, you talk to the people over there, and they're just, why would you do this? Well, because it saves cost. My background is actually aeronautical engineering, and I figured out, even when I was in college, how to save a lot of cost on airplanes. You just leave the left wing off. It saves a lot of cost. It doesn't fly very well, but saves cost. Okay, don't do plateless staple up. And obviously, slab on grade, we can get to low temperatures. We want low resistance floor coverings. And the under slab insulation. Over the years, I think, Robert, you and I have seen the bubble foil, and we've seen other stuff going down. Here's the question. If you don't get under slab insulation right the first time, how hard is it to retrofit under slab insulation? You got one shot in the life of the building, practically, to do it. Do it right, okay? At least 2 inches of extruded polystyrene, maybe even more if you're going for something like, you know, passive house ratings. Thermal mass on heat emitters. There's a huge range. As you'd expect, the slab is a very high thermal mass relative to the other emitters there. The fan-assisted panel radiator there in the lower right is about 1% of the thermal mass of that slab. Why is that relevant? Response time. Low energy buildings, as I mentioned, internal gains can make things change quickly in terms of temperature. You need systems in a building like that, especially where there's going to be significant solar gain or people gain, you know, heat gain from people, lights, equipment. You need systems that can adapt quickly to that. They need to be able to turn off the heat as fast as you turn on the heat. Otherwise, you're going to get into overheating. So imagine a house full of south-facing glass with a 6-inch concrete slab. It's, you know, the comfort is not going to be there because the slab's always going to be overshooting in the morning and probably undershooting in the evening. So low thermal mass tends to be better for low energy buildings. Air to water. We've got several air-to-water heat pumps here. I'm delighted to see that. This is a product category that I think is going to become very important in the hydronics market. I think eventually this could eclipse geothermal in terms of numbers because it goes in without the earth loop, and that's a huge savings. So real quickly, what is it? Well, you're all familiar with these air source units, and you're familiar with geothermal, water to water. So all we're doing with an air to water heat pump is we're basically using the air side of heat pump technology for source, and we're using the water side for delivery. Okay? You can set them up. Typically, they're going to be set up with antifreeze. Most manufacturers are going to mandate the use of antifreeze because if we have water in an outside unit, obviously in a long-term power outage, it could freeze. You can either set up the whole system with antifreeze or you can put a heat exchanger between the heat pump and the balance of the system. I would recommend the first one, the top one. Put antifreeze in a whole system. With the heat exchanger, you're inducing a performance penalty on the heat pump. You're forcing the heat pump to run several degrees warmer than it would have to run if the heat exchanger wasn't there. You have to do that to drive the heat through the heat exchanger. Either one's possible, but in general, the better performance is going to be where you don't have the heat exchanger. Again, there's several samples here to take a look at. These are called monoblocks. They're self-contained, pre-charged with refrigerant. You set them up, 2 pipe connections, electrical connections, and you're ready to go. You don't need refrigerant skills or tools to set these up. Okay? There's what's called hydro split. There are a couple units on the market now. Enertech and Taco both have these units. This is where you have an outdoor unit and an indoor unit, and it's not refrigerant running between them. It is antifreeze. Okay? Hydro split. And then there's also a DX or refrigerant split. This is like a standard AC unit where you've got an indoor and an outdoor unit and you've got refrigerant tubing between them. So you would need some basic refrigeration skills and tools to set these systems up. Here's a Canadian product, Nordic Heat Pumps. It's built over in Maritime, Canada. And it's a split system. The thing that's different about this design, just to show you some variation, they put the compressor inside, which means we can also do a de-superheater for domestic hot water. And it also brings the electronics and the more vulnerable electrical components inside. So it kind of caught my eye. It's, again, it's produced Eastern Canada. I can't think if it's Halifax area, but... And by the way, the latest issue of HPAC magazine had an article where they used 3 of these up in, see if I get this pronounced right, Nunavut. I'm having none of it. Anyway, it's a cold climate, about 8,500 degree day climate, and it does have electrical backup, but it just shows that you can do this in a cold climate. Global heat pump market's huge, 4 million a year. Most of that is going, half of that's going into China, okay? European market, 690,000 units in 2019. Italian market, the last statistic I saw was 150,000 units a year. This is a very big business in the more traditional hydronic areas, the Asian market and the European market. And as has been the case over our careers, a lot of the European technology tends to work its way over here, okay? And again, there's strong growth. And I just put some manufacturer names up there. I'm sure you recognize many of those names. These are companies that are selling ductless mini-split systems in North America. They all have air-to-water heat pumps. They just haven't, some of them haven't chosen to put it in the North American market yet. But I do think you're going to see that changing. I can virtually guarantee it. Performance simulations. Now, this is a house in upstate New York. We did some performance simulations. Anybody know where Plattsburgh, New York is? Plattsburgh's way up there at the tip of New York State, and it's about an 8,000 degree day climate. It's cold. And so we did performance simulations on air-to-water heat pumps. And I'll cut to the quick. We're seeing COPs, these are average COPs, between about 2.6 up to, well, I'm sorry, what does that say? 2.8 down to about 2.6. And this is basically the supply water temperature required at design load. And I'll cut to the quick. The takeaway is you can use an air-to-water heat pump with a baseboard system. But you need to have supplemental heat in some form. It could be the existing boiler, it could be a new boiler, it could be, anything that would provide supplemental heat, and you need to use outdoor reset control. And you're still going to get, even, over here we're showing percentages of the seasonal space heating energy that's being supplied by the heat pump. And even if your system needed 180-degree water at design with outdoor reset, we can do about 90% of that load. Now that's a 4-ton rated heat pump, like the units that are here, nominal 4-ton, in a house that at design load is 36,000 BTUs per hour. So you might say, well, it's an oversized heat pump. The sizing of a heat pump isn't quite the same as sizing a boiler. You can put a 4-ton heat pump in a 3-ton house, especially now with inverter compressors. The compressor can adjust for the load. But the takeaway, 2 takeaways, you're going to do better at low water temperatures, and it's not a throwaway to say, here's a baseboard system, I can't put an air-to-water heat pump in there. You can. Your performance is going to be lower. Now, there's things you can do to bring those performance numbers up. You can insulate the building. Anything that brings the load down will bring the water temperature requirement down and bring the performance of the heat pump up. The other thing is you can add heat emitter surface area, as Robert was saying. The more surface area you have, whether it's baseboard, panel rads, radiant ceiling, whatever, it can be a combination of these emitters. As you increase total surface area of your emitter system, the water temperature goes down. And you may have opportunity to modify those distribution systems by adding more heat emitters. You may have opportunity to weatherize the building, or maybe it's a combination. But even without the weatherization or the added heat emitters, we're still in that range. I'm going to say 2.5 up to maybe 2.8 for seasonal COPs in a cold climate application. And this is rivaling where geothermal systems are. It's not quite as good, but it's approaching it. Okay, and I just want to show you, these are our costs in upstate New York now. At 16 cents a kilowatt hour and an average COP of 2.75, we're at just under $20 per million BTUs delivered. And that's competitive with where gas is right now. Gas prices are fluctuating wildly. Propane is way up there. Last winter in upstate New York, propane was $5 US per gallon. And fuel oil got as high as, it went over $5 a gallon. It fluctuates. But I want to show you that energy supplied from an air-to-water heat pump in a cold climate is competitive against other fuel options. Retrofitting, okay? Don't throw away the boiler is the takeaway here. I've talked to people that they have very good ideals in mind, but they hate fossil fuel. They absolutely think fossil fuel is the scourge of the earth. And the first thing they want to do is rip out a boiler. If the boiler has service life left, leave it in the system. It could eventually go away. Maybe it's replaced by something else. Maybe it'll be replaced by an electric boiler. But it's backup, it's supplemental heat, and really importantly, you can run a boiler, residential boiler, on a very small little backup generator. Like a little Honda generator you could set on a table. That would run a hydronic system. As long as you keep gas in the generator, your house isn't going to freeze. That's resiliency, okay? And the other thing is having a boiler in a system, having what we call a dual fuel system, it opens the opportunity for what are going to be very creative electrical utility rates. You're going to see real-time pricing, off-peak rates. I just talked to some people up in Maine. They have so much wind generation in northern Maine, there's actually times when they were paying customers to take the electricity. They had negative electric rates. But even without the negative sign, if you're buying electricity at 1 or 2 cents a kilowatt hour, okay, that's when you want to run the heat pump. If you're paying 25 cents a kilowatt hour on peak, that's when you want to run the boiler. So it opens the opportunity for a system like this to integrate with what the utilities are likely to do. Utilities are trying to shift the load from peak to off-peak periods. And those rate structures need to have some kind of mechanical system that's compatible. Real quick, I'll run through these things. There's an air-to-water heat pump, a monoblock. It goes into a buffer tank, and over on the upper right is a manifold, some PEX tubing, and panel rads. There's a variable speed circulator right here, all right, that just goes up and down as the thermostatic radiator valves open and close on those radiators. It's really a simple system. It's a heating-only system, though, okay? So it's a very basic system. Now here's where we've kept, or we've put a new boiler in the system. It's just the boiler's in parallel with the heat pump. And your control system decides which one operates, or possibly both at the same time. All right? It's just in parallel. So either the boiler or the heat pump can inject heat into that buffer tank, and that tank's actually what we call a three-pipe buffer that could basically allow heat to go directly from the heat source out to the load if they're both operating at the same time. That looks like a pipe, but it's not. It's a vent that's not connected right there. So this is the takeoff right here for the hot water. Here's where we're adding a air handler for chill water cooling. So now you see there's a diverter valve, and it simply steers the output from the heat pump in heating mode. It goes up to the buffer tank. In cooling mode, it goes to the air handler. We've got a tank here with internal coils. There's a tank over there with internal coils if you want to look at it. That can serve as domestic water, preheat, or complete heat, depending on what temperature you maintain that tank at. And I'm showing a backup for domestic hot water. That would be necessary if you're using outdoor reset control on the water temperature in the buffer tank. And our simulations have shown that is better than maintaining the buffer tank hot enough all the time to completely heat the domestic hot water. That was one of the kind of the big questions I had. Are we better to use outdoor reset and have more direct electric resistance heating of domestic water? Or are we better to maintain the tank at a higher temperature all the time using the heat pump and have a slightly lower COP from the heat pump? Well, the outdoor reset control wins, okay? This just shows you, so I'm going to talk about this more this afternoon. I won't spend a lot of time on it here, but this integrates space heating, cooling, domestic hot water heating, and heat recovery ventilation. I'm a big proponent of hydronic professionals adding heat recovery ventilation to their offerings. Now you've got a complete system. You're dealing with the heating, the cooling, domestic water, and you're dealing with a very important thing, indoor air quality. Okay? So that's a complete system offering. Again, I will talk about this more this afternoon, how we put it together, but this is a system where the panel rads are running on 90-degree water in February in upstate New York. Here's kind of a unique application. This is where you've got a slab-on-grade building. Think about a Midas muffler shop. Do you have Midas muffler up here? Vancouver? Okay. Midas, any kind of a commercial slab-on-grade, new construction, radiant floor heating. You don't need a buffer tank. You've got huge thermal mass in that concrete slab. So you can just connect a hydraulic separator between the heat pump and the radiant floor, keep the system really simple, use constant circulation in the floor, and just run the heat pump as a heat injector into your distribution system. So here's a final thought. So we're combining load building envelopes, all right, with modern hydronics technology, the state-of-the-art circulators, panel radiators, whatever, plus heat pumps, whether it's a geothermal water-to-water or an air-to-water heat pump, and we're getting energy cost savings, certainly. Superior comfort. We can never, as an industry, downplay the importance of comfort. We hear the efficiency words, the AFE, AFUEs, COPs, all this. Comfort matters. Comfort should be at the top of the list. And if we forget about that, if we get pulled over into this, my COP is better than your COP type of thing, we're going to lose the market. We have to sell what we do best, and that's provide comfort. And finally, carbon reduction. So this is a formula that it brings together all the trends that are happening in the market, and it allows us to take hydronics into this market and be in a very good position. We need to get that message to builders, to politicians, okay, and also to energy office people. I've been working with a lot of different state energy offices. They have really no idea. If I say distribution efficiency, no idea. They are very hung up on things like AFUE, SEER, COP. That's their word. They just assume that we can drop a heat pump into whatever and it's going to work, and that's not the case. We have to make our distribution systems compatible with those heat pumps. I guess, do we have any time for questions, or are we? No. We're done.
As I said earlier, these guys are the hydronic superheroes, and you can kind of figure out why they've earned that title. And we definitely appreciate this, and we're so glad that you guys reunited at our event. So thank you very much, and thanks to the folks at Uponor for helping out on that as well. Ladies and gentlemen, Siggy and The Bean.